Hello, chemist and biochemist. In this video, what I'd like to talk to you about is protein structure and the different levels of protein structure. In addition to talking about those individual levels of protein structure, I'm going to talk about some of the forces that hold those proteins or hold those different structural levels together. All right. So the great thing about molecular biology and biochemistry and biology, and well, I'll say chemistry as well, is sometimes you encounter, I guess, people who are in charge of naming something that they're not extremely creative. They are very direct and to the point. And well, our different levels of protein structure kind of follow that same mold. We have the primary structure represented by one knot, the secondary structure, tertiary structure, and the quaternary structure. Now, your primary structure is represented by simply the amino acid sequence. So the amino acid sequence of a peptide, a polypeptide, a protein, reading from the N termini to the C termini. That constitutes your primary structure. Now, the forces that hold this together are peptide bonds. So although it identifies the N-terminal amino acid, we don't, whenever we're talking about the primary structure, worry ourselves with, well, is that arginine going to have an impact on a lysine or an aspartic acid somewhere else in that protein or in that polypeptide? We don't care about that at this point in time. Our secondary structure is also where you're going to find kind of what are known as local structures. So local structures. So you see a little bit more organization of RE, a little bit more organization of the polypeptide and of the protein, but it's kind of in its infancy. It's a developing structure, a developing molecule. These local structures, what are the most common local structures are your alpha helices and beta sheets. So how these polypeptides kind of arrange themselves in 3 dimensions, or in basically 2 dimensions. Now, the forces that hold these together are going to be backbone, H bonds. So if you think about a peptide bond, what you have is something that looks a little bit like this. H, here's a peptide bond. O. Okay, so what you have there with a carbonyl oxygen and hydrogen off that nitrogen there is you have a prime example for a hydrogen bond acceptor and a hydrogen bond donor. So this would be our donor, and this would be our acceptor. So your local structures are largely going to be dictated by your hydrogen bonds or backbone hydrogen bonds. Now, where it gets a little bit complicated is do the identities of different amino acids in a polypeptide sequence, do they have an influence on the secondary structure? They do. They do have an influence on secondary structure, but they're not going to dictate it in the same way that your beta sheets your backbone hydrogen bonds are going to dictate the secondary structure. Your tertiary structure of a protein is the 3D structure. So when we talk about an X, Y, and Z plane, what does that molecule look like in 3 dimensions? To be honest, whenever I think of protein structure, what I always use as a model is basically a crumpled up piece of paper. Now, whenever I look at that piece of paper, I see that, well, it's got space vertically for my y-axis, laterally for my x-axis, and then forward in, well, basically in this 3rd dimension, in the z-axis. And your tertiary structure is going to be influenced, or is going to show what does this whole polypeptide look like in 3 dimensions and all these different angles. Now, the structures that are going to hold that together, well, they are R group interactions. So examples of that would be, well, you could have ionic interactions between 2 R groups. For instance, an arginine and aspartic acid, you have positively charged residue and negatively charged residue. You could also have hydrogen bonds between, say, a serine and a water molecule and another serine or a threonine or something of that nature. So those R group interactions, how those interact, you've got covalent and non-covalent interactions going on. The quaternary structure is, it always feels a little bit like, well, it's a little bit redundant, but it's not quite, because this is the 3D structure of multiple polypeptides. So how do these different polypeptides interact in 3D space? So again, with the model of you have a piece of paper crumpled up. Well, if you have two pieces of paper crumpled up, the quaternary structure is visualizing those two proteins together. What sort of interactions hold those together? And the interactions between those are primarily your R group interactions. Does that mean that a quaternary structure cannot be stabilized by some sort of backbone interactions or a backbone R group interaction? No, it absolutely can be. But it's going to be how these two subunits meet and dock and basically hold together. So at any rate, I hope that was helpful. I hope this gives you a better understanding of the different levels, the hierarchical structure of proteins and polypeptides. Each one of these levels builds to facilitate the next level. So it's important to remember that, yeah, your tertiary structure is dictated by R group interactions, but that's not to say that it has no, or it's not standing on the shoulders of peptide bond interactions. It's just that the primary influencer of what the 3D shape of this molecule is those R group interactions. It kind of takes for granted almost the backbone interactions and peptide bonds. All right, well, I hope this is helpful, and I hope you have a good one.